When is a relation R called a partial order? So from the term partial order itself, we know that it is something related to ordering, right? We often use relations to order some or all of the elements of sets. For instance, we order the set of integers using the relation consisting of the pairs x, y, where x is less than y. When we add all of the pairs of the form x, x to the relation, we obtain a relation that has these properties, which are reflexive, antisymmetric, and transitive. These are properties that characterize relations used to order the elements of the sets. So a relation R on a set S is called a partial ordering or partial order if it is reflexive, antisymmetric, and transitive at the same time. Okay, a set S together with a partial ordering R is called a partially ordered set or a poset. It is denoted by S, R. Okay, members of the set S are called the elements of the poset. Here is a question. Is greater than or equal to relation a partial ordering on set of integers? So the question is, the relation here is the greater than or equal to relation, and the set is the set of integers. Okay. Now we want to see whether it's a partial ordering or not. So let's see whether it is reflexive, antisymmetric, and transitive at the same time. So if you take any A belongs to the integer set, we have that A is at least A because A is same as A, right? Hence the relation is reflexive. Now suppose that A comma B belongs to the relation R. Okay, meaning that A is at least B. And suppose also we imagine that B comma A is in the relation, implying that B is at least A. So when we suppose A comma B belongs to R and B comma A belongs to R, we get that A is at least B and B is at least A, which implies that A equal to B. And that's what the definition of antisymmetric relation itself, right? Hence the relation is antisymmetric. Now suppose that A comma B is in the relation and B comma C is in the relation, implying that A is at least B and B is at least C. It implies that A is at least C, right? So A comma C belongs to the relation, and hence the relation is transitive also. So we have reflexive, antisymmetric, and transitive. Now so the relation is partial order. Okay, next we ask, is the divides relation on the set of positive integers a partial ordering? Let's see. If you take any element A comma A belongs to R because A divides A, right? And hence the relation is reflexive. Now suppose that A comma B is in the relation and B comma A is in the relation. Implies that A divides B and B divides A. So when A divides B and B divides A, it has to be the case that A equal to B, and hence the relation is antisymmetric also. Now suppose that A comma B is in the relation and B comma C is in the relation, implying A divides B and B divides C. So B equal to A into K and C equal to B into P, where K and P are integers, positive integers. Now C equal to A into K into P, right? So it implies that A divides C. So A comma C is in the relation and hence the relation is also transitive. So we have the partial ordering relation here because it's reflexive, antisymmetric, and transitive. So the divides relation on the set of positive integers is a partial order. Now we know that the set of positive integers comma the divides relation, the set plus comma divides is a poset, right? It's a partially ordered set because the divides is a partial ordering relation on the set of positive integers. Now you take two elements 2 and 3. 2 is not related to 3 and 3 is not related to 2 because 2 doesn't divide 3 and 3 doesn't divide 2, right? We have two elements A and B here where A is not related to B and B is not related to A. So that's the point. The elements A and B of a poset S comma less than or equal to are called comparable if either A is less than or equal to B or B is less than or equal to A. Meaning that if you take any elements A and B, A should be less than or equal to B or B should be less than or equal to A when the relation is less than or equal to. Okay. So when either A is related to B or B is related to A, we say that these two elements are comparable. Now, if A and B are elements of the set S, but neither A is less than or equal to B nor B is less than or equal to A, it means that A and B are elements which are incomparable. So if neither A is related to B nor B is related to A means A and B are incomparable. So that's the definition for comparable and incomparable. So when we say a partial ordering, the adjective partial is used to describe partial ordering because pairs of elements may be incomparable. Like as we saw, set plus comma divides is a poset, but A and there are two elements 2 and 3 which are not comparable, right? Now, if it so happens that every two elements in the set are comparable, then the relation is called a total ordering. Now, if S comma less than or equal to is a poset and every two elements of S are comparable, then S is called a totally ordered set. So the partially ordered set becomes a totally ordered set when every two elements in that set are comparable. Alright, now the relation less than or equal to is called the total order. A totally ordered set is also called a chain. Okay, so chain is another name for a totally ordered set. Now we ask whether the set of integers comma greater than or equal to relation a totally ordered set. It is a totally ordered set because you take any two elements A and B, it is the case that either A is at least B, either A is greater than or equal to B or B is greater than or equal to A. So set comma greater than or equal to is a totally ordered set. But set plus comma divides is not a totally ordered set because there are two elements 2 and 3 which are not comparable, right? Now, S comma less than or equal to is a well-ordered set if it is a poset such that less than or equal to is a total ordering and every non-empty subset of S has a least element. So, if the set S together with the relation R has to be a well-ordered set, then it has to be the case that the set S together with the relation R has to be a partially ordered set such that the relation R is a total ordering. And it also has to be the case that every non-empty subset of the set S has a least element. If this is the case, then we say that the set S together with the relation R is a well-ordered set. Okay, so we have seen today in this video partially ordered set, totally ordered set and well ordered set.